first thing I want to establish. And the next thing is what? If I multiply either of them by some constant C, I should be able to move the constant out of the operator. Alright, so that is do you get that? So again I will say what? This is the second part. This is the first part of the group. I've used that to establish that first part is correct. Then the second part of the proof is to show that T of C V1. So if I have C V1, what is it going to be? That is going to give me 1, 1 minus 1, 2, 4 multiplied by what? C V1. So what is C V1 going to be? So C V1 will be, if I'm multiplying the matrix by a constant, it's the same thing I'm multiplying all the elements of the matrix by that constant. Is that clear? So this will be equal to C. So V1, this will be C A1, C B, sorry, C A, C B, C. Let's not use C here, let's use K. That's what constant K. So we don't need to stop with this. So the K, B, K, space, and K. So that will be our results. Is it clear? So basically I can move this out of the expression. So I can say obviously this is equal to 1 minus 1, 2, 4 multiplied by, so I can move out the K into A, B, C, D. How I multiply the K doesn't matter, I can move it outside. Is that clear? Alright, so at the end of the day I can write that this is equal to this is equal to K into 1 minus 1, 2, 4 A, B, C, D. So therefore it follows that K, what I have is equal to K multiplied by T of V1, because what I have is T of V1. So I'm able to establish that T of KV1 is equal to KT of V1. So S is a linear number because it satisfies the two conditions. C is a linear number. That's how to complete the proof. If you have not completed your fee, you are not meant to be here at all.
Thank you.
K-E-R-N-E-N. Kernel of linear map.
As I get to reading it, some company that get
Hello, listen.
to
mapping V to W. Right. We won't see mapping V to W. The set of all x, elements of V, the set of all x elements of V, such that T of x equals 0, the set of all x elements of V such that T of x equals 0, such that T of x equals 0, is called the kernel of T. It's called the kernel of T. The set of all x elements of the domain V is such that T of x equals 0 is called the kernel of T. And written as KERT, as KERT, and written as KERT. The set of all x elements of V such that T of x equals 0 is called the kernel of T, and written as T. Right, so that means that, listen very well, listen. The kernel of a linear map is the set of those elements in the domain. You know what I mean by domain now? Just like the function has a domain and the function. This is the domain of the function. It takes, or the transformation, it takes elements of vectors in this vector space and gives vectors in this vector space. Is it clear? So the elements in this vector space that will yield 0, okay, the 0 element of the vector space W are those when you put them together, they form a set which we call the kernel of T. Please pay attention. We have said that please listen now. We have said that if the transformation is linear, we have said for a linear transformation, T of 0 is equal to 0. I remember that T of 0 must always give 0. That is what makes it. Okay, one of the things we should expect from a linear transformation is T of 0 must be 0. At least if you have a transformation given to you and T of 0 is not 0, there's no need to check other properties. Just move on. It is not linear. Do you understand what I just said? Alright, but that does not mean that there cannot be other elements whose transformation will be 0. You see what I just said? We know that T of 0 is 0. There could also be other elements which, when transformed, will give us 0. Is it making sense to you at all? You understand what I just said? Alright. So you know 0 here will be the 0 element in the and this 0 will give the 0 element in the that's what I'm saying, right? Alright, so it could be, for instance, a map that takes elements, let's say this map takes elements from the space R3 and gives elements in the space R2. That means T of the 0 elements in R3, okay, must be equal to, or must be equal to 0 elements in R2. Do you understand this idea? Alright. That is for the 0 elements. Now there are also other elements which, when you carry out the transformation of them, they will give you the 0 elements in the codomain. So when you put all those elements together, you form what we call the kernel of T. Is it clear? Okay, this is synonymous to what we call zeros of a function. You know, 0 of a function. 0 of the function means those numbers which, when you put into the function, will give you 0 results. You know what I just said now? That is 0 of the function, right? So we also have like zeros, just that we don't call them zeros here. We also have zeros of a linear map, right? But we don't call them zeros. Rather, we call the set the kernel of the map T. Right? So how do you get the kernel of the map? Yeah, you know a linear map. So let's take some examples. So see what I'm talking about. Example 1. Please pay attention. Find KT, that's KERT. Find KT where T maps R3 to R2. Where T maps R3 to R2. Where T maps R3 to R2. Okay, where T maps R3 to R2. is defined by T of x1, x2, x3 equal to x1 plus x2, x2 minus x3. Please pay attention. So that is the definition of the map. Is this map linear? Is this map linear? Is this map linear? Yes. We're dealing with linear maps. This one is one that I'm trying to let you tell you to check for. Definitely it should be linear. Is that clear? Alright. So we want to find out the set of all elements. Please pay attention. You know, that set of all elements that will give you 0 elements of the codomain. We actually form another subspace. We can form a subspace of V, because it is not all the elements in V that you can put in and get 0 elements in W. So those ones that you can put in and get 0 elements in W, they will actually form a subspace as we get to see now. Okay, so let's move on, please. Look at this now. So we said that, please pay attention to this. Pay attention. So based on the definition of solution now, based on the definition of kernel, we are saying kernel contains those elements in W, okay, those x elements of V, such that T of x will be equal to 0. Is this clear? Alright, so in this case, please listen very well. I can say that let x equal to x1, x2, x3 be an element of car T. So if it's an element of car T, what does that mean? That means that T of x must be what? Equal to the 0 element in the domain, in the codomain. Is that clear? Must be equal to the 0 element in R2. Is it making sense to you? Okay, what is T of x? T of x is defined this way. That means I should have my x1 plus x2, x2 minus x3 to be equal to, what is the 0 element in R2? What is the 0 element in R2? Let's look at now. I can't plug you around. Say you know. I can't plug you around. Say you know. This is 0, 0. Alright. So we want to find what will be the condition under which this will give us sharp leg. Definitely 0, 0 is a member of car T. So car T can never be empty. Do you understand that? You are dealing with a linear map. Car T can never be empty. 0 element is always there. Is it making sense to you? Right. So we said that, listen please, listen. So this is going to give us what? So this means that x1 plus x2 should give us 0, and then x2 minus x3 should give us 0. Is this clear? Okay, so these are the 2 elements we have here. You can see that we have 2 equations, but we have 3 unknowns. Abi? We need x1, x2, x3, but we have 2 equations only. Is that clear? That means we have how many free variables? 1 free variable. Abi now? Alright, so that means in this case, I can set x3 to be equal to k. Set x3 equal to k. Now if they were more, maybe you have 3 equations and 3 unknowns, you know, you should do row reduction, I mean now, to have it in echelon form so that you can have a simplified equation. But here we just have 2 and then we have 3 unknowns. You can just move on. Please listen very well. So if you set x3 equal to k, that means what? x2 will be equal to what? x2 will be equal to k, this left, from this equation. And the next one will be equal to what? Minus k. x1 will be equal to minus k. S, please pay attention. X, k, will be equal to minus k, k. Clear? That means that x will be equal to k minus 1 by 1. Does it make sense to you? Do you understand that? Do you understand that? Alright. K can be any real number. Abi? That means whatever real number you set k to be will actually satisfy the condition. Is it clear? So k can be 0. If k is 0, that gives us the 0 element, which is a member of car T. If k is 1, it gives us minus 1, 1, 1, which is also a member of that. Is it clear? Exactly. That means that this will be given by this element, will be given by this expression. That means our car T, this by that means that car T, don't forget that car T is a subspace of B. Why R is the subspace of B? You can see that it has this listen now. Its elements are all members of R3. Okay, V is our domain. Our domain is R3. Its elements are all members of R3. Okay, I mean its elements or all its vectors are members of R3. Is it clear? But then there are members in R3 that do not belong here. Is it making sense to you? Alright, so it's actually a subspace of R3. Alright. How do I get to the subspace? Definitely you can see that the zero element is a member of it. One of the conditions is that the zero element has to be a member of it. You can test the other condition to see that it satisfies it. Alright, so car T will be equal to, please listen out, it will be equal to the subspace containing elements x1, x2, x3. Please listen very well. Okay. Such that this will now be given by this, we are going to say containing elements x. This contains elements x or vectors x in R3 such that s is equal to k minus 1, 1, 1 for all real k. That about that. That means you can set k to be any real number. That's the definition of your RT. Is it clear? So with that, you can get any element that is a member of RT by setting k to be any real number. Is it clear? Is this clear? Alright, so listen very well. So you can see that. Now let me ask you something. Now what is we know that car T is a subspace of R3. So if I ask you what is the basis or what can you find a basis for car T from this result? What is a basis for car T that you can obtain from this result? You know the meaning of basis? You know the meaning of basis? This thing is so simple. Is it that there are okay, I think there are too many definitions here. So yeah. What's the meaning of basis? Oh yeah, you can check your you can do. What's the meaning of basis? What is the meaning of basis? Is it basis?
No, you need to not compare this for basis.
So car T, okay, car T is a vector space. That clear? It is a subspace of R3. You can see it is a subspace of R3. Please pay attention. Car T is a subspace of R3. Listen very well, listen. Hello, listen now. So this tells you that listen, basis is a set of linearly independent vectors that span the space V. That is the basis of the vector space V. Is that clear? Alright, so what will be the basis, or say a basis of car T will be what? A set of linearly independent vectors that span car T. Now, do you understand what I just said now? What's the meaning of span? That means that I can write all elements in car T as a linear combination of the elements of that set. Is it clear? Can you remember that? Alright, so obviously, you can see that I can write all elements in car T as a linear combination of this single vector. Do you understand what I just said now? I can write it as a multiple of this single vector. Is it clear? So, definitely, it says S equal to minus 1, 1, 1 is a basis of T. Is a basis of does that make sense? This set is a basis of is that clear? That set is a basis of T. You know that a set it can be empty. You understand that? The set can be empty. A vector space cannot be empty. We have said that. Vector space to contain or consider at least the zero element. The vector space cannot be empty. But the set can be empty. The set can contain only one element. The set can contain only two elements. Is that clear? So this is a basis of this vector space. It has only one element. It's still a set. Because we have said basis is a set of vectors that span the vector space B. Is it making sense to you? Okay. So this set actually span the vector space B. And the vector space Kt, because I can write every element in Kt as a linear combination of these sets. Okay? That is that. So that means, so what is the dimension of Kt? What is the dimension of Kt? Two weeks to exam. What's the dimension of Kt? 3. 1, 3. 1 or 3? 1. I think it is 1. Let me see your hand. Oh yeah, now, yeah. I will not give you a wrong.
1.
We don't see how. It is 1. Let me see your hand. Okay. You think it is 3? Let me see your hand. I'm not sure. I'm not sure of the field. Let me see your hand. You don't know it at all. The dimension of the vector space is the number of vectors in its basis. You understand that? Together. Any basis you have for it. That means the number of vectors in any basis of the vector space is unique. You get me? That's the dimension of this vector space. The dimension of this vector space Kt is what? 1. Because there's only one vector in its space. Is that clear? So any basis you want to find for this, you have only one vector in it. Is it clear? So that is that about that. Can we move on? Can we move on? Alright. You want yourself. Alright, so you can also write this. You can also write this as span. Please pay attention. Span of minus 1 over 1, 1. You get that? Span of minus 1. That's vector space generated by multiples or linear multiples of that set. A linear combination of that set. That's the part. You can define the any way. That way. Alright, please rise. The kernel of a linear map. The kernel of a linear map. The kernel of a linear map. No, not the question, The notes. The kernel of a linear map is a subspace of the domain. Is a subspace of the domain. Is a subspace of the domain. Alright. On the next line, right. The dimension of Kt, is called the nullity of T. It's called the nullity of T. The dimension of Kt is called the nullity of T. Nullity, nullity of T. Thus, for the example above, the nullity is 1. The nullity is 1. The nullity is 1. The nullity is 1. Alright, let's move on. Example, another example. You're going to solve this yourself and we'll solve it together. Get this yourself. Calculate the nullity of the linear transformation. Calculate the nullity of the linear transformation. So listen now. If you have this kind of question, what do you think you want to do? You want to get the car T first, Abi, and find out how many elements, Abi, how many vectors we made in its basis. Is this clear? I mean, so we're going to do exactly what we just did now, just that we are extracting a different information from it. Is this clear? Right. What we just did now is to actually just define the car T. So this example, our final answer is this. This is our final answer. Because we just want to find the kernel of the vector space. And that is the definition of the kernel of that vector space. Okay, you can use X mark. So that you get different spaces, but it doesn't matter. So let's move on. So basically, calculate the nullity for the linear transformation T for the linear transformation. Calculate the nullity for the linear transformation T maps R3 to R2 defined by calculate the nullity for the linear transformation T maps R3 to R2 defined by T of A, B, C is equal to A plus 2B plus C to minus A plus 3B plus C. So give it a try. Calculate the nullity of the linear transformation of this. Full stop. Add this. Find a basis for car T. Find a basis for car T. Find a basis for car T. This is exactly, we're going to solve this the same way we solved the first one. The same processes, and you extract the required information from it. The only difference is that what? The only difference, please pay attention to this. The only difference here is the definition of the transformation and then the symbols used. Okay, here you have seen, you can see A, B, C instead of X1, X2, X3. So it doesn't make any difference. Do you understand that? Okay, so that's just difference in symbol. So still the same interpretation, the same processes, and the same information to be extracted from the results. So go ahead. Give it a try. Go ahead. If you set C equal to K, it's fine. If you set C equal to K, but it's because at the end of the day you still have to solve the simultaneous equation for A and B. Instead of doing that, you can carry out row reduction. Do you understand that first? So that you can reduce at least one of them to having only two elements. Do you understand what that does? Did you get that? So you do that first. Reduce one of them so that you carry out row reduction so that one of them will have only two elements, so you can get the result directly. And substitute with the other one. Do you get it? Oh yeah. Listen now. Select X equal to A, B, C, the sub-elements of car T. Not clear? Then it will follow that T of X, which will now be equal to T of A, B, C, will be equal to 0. Happy? So we are going from R3 to R2. So the 0 there will be the 0 of R2. Is that clear? Alright, so that means I should have T of A, B, C, that is A plus 2B plus C into minus A plus 3B plus C is equal to 0, 0. Is that clear? Yeah. This is what I have. And if we put out this equation, let's have A plus 2B plus C equals 0, minus A plus 3B plus C equals 0. You can put this in matrix form. 1, 2, 1, minus 1, 3, 1, multiplied by A, B, C equals to 0, 0. Is this clear? So the augmented matrix from this will be what? Will be 1, 2, 1, minus 1, 3, 1, to 0, comma, and 0. You know, you can do without the 0. If included in this file, if it needs included in this file. So we have, when we put this in row reduced form, you can see the first element here is already 1. So there's nothing to do to that. The only thing we want to change is this one. I mean, make this 0. And how do you do that? R2 plus R1. I mean, alright, so we're going to say that R2 is equal to R2 plus R1. So that's going to give us what? That's going to give us 1, 2, 1, 8, 0, 5, 2, 0. Back here. What's the next thing to do? What's the next thing? Reduce what to what? 5 to 1. Happy? So, reduce 5 to 1. We divide this by 5. Happy? R2 is equal to R2 upon 5. This will give us 1, 2, 1, 0, 1, 2 over 5, 0, 0. Okay. What's the next thing? Make this 0. That will be what? R1 equal to R1 minus R2. That's going to give us what? 1 to become 0. 2R2, that's 4 over 5, right? So 1 minus 4 over 5, 1 over 5. And I still have 0 here. This is going to give us 0, 1, and 2 over 5. So that is all half. It's now in row reduced form. So we can put back our answer. That means, therefore, I can have A plus C over 5 equal to 0. And B plus 2C over 5 equal to 2. Is that clear? So from here, I can now say what? Set C to be equal to K. C is equal to K. K will be equal to minus K over 5. And B will be equal to minus 2 over 5. With this, we can write out our final result. So that means what? T is defined as follows. Listen very well. So that means S is an element of class which is A, B, C, will be equal to is A is what? Minus K over 5. B is what? Minus 2K over 5. And C is K. This will be equal to what? You can bring out K, you can bring out K over 5. Anyone you want to just factorize. This is going to give us K into 1 over 5. Minus 1 over 5 minus 2 over 5. And 1. You can have it this way. You can bring out 5 as well. Anyone you please. Is it clear? Alright, so this is going to give us our T. So you can now write that S T is a vector space that contains elements X, A that belong in R3. That is, they are three-dimensional vectors. Is that clear? Such that X is equal to K into minus 1 over 5 minus 2 over 5, 1. And K is any real number. Is that clear? Or alternatively, you can write that as T is equal to the span of this vector minus 1 over 5 minus 2 over 5 and 1. So anyone you write is fine. The span of this, that is all vectors that will be linear multiples of this vector. That will give you the element of this. What is the question? The question says, listen please, this is a by the way answer. The question asks for the nullity of T. Abi? So what is the nullity of T now? What's the nullity of T from this result? 1. The nullity of T is the dimension of its basis. Abi now? Or the dimension of T. Or T rather. That's the nullity of T. So So why that the nullity is usually given by this symbol. Nullity of T because the dimension of car T is from 1 to 1. That's left from this result. And a basis for T for car T. A basis for car T is S equal to minus 1 over 5 minus 2 over 5. Listen very well. If this were an OBJ question, If this were an OBJ question, and you don't find, you may not see this in the option. You may see other things like stuff like minus 1 comma minus 2 comma 5. Right? You also see something like 1 comma 2 comma minus 5. Pay attention. Hello, look at the board. You can see that they are the same. Do you understand this? Alright. You can also see something like this. You can see something like 1 over 2 comma 1 comma minus 5 over 2. They are the same. Is it clear? They are all linear works of this. Is it clear? Yes. Alright, so you see any one of them in the option. You make it sense. Depending on what you have factorized, do you understand this? That's that. That is a basis. That's why we call it a basis and not the basis. A basis means you could have different bases. Is it clear? Just that the dimension, the number of elements in the basis is always unique. The number of elements in the basis of the vector space is always unique. And that is the dimension of the vector space. So the dimension of car T is the nullity of the transformation C. The dimension of car T is the nullity of the transformation C. Another example, give it a try. Another exercise. Find the listen. Determine car T and find a basis for each of the following. Determine car T and find a basis for car T. Determine car T and find a basis for car T for each of the following linear maps. For each of the following linear maps. For each of the following linear maps. So, number 1, C maps R3 to R3. Okay? Defined by T of x1 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 minus x2 x2 plus Alright, so work on these special results. Everybody. If you don't get this one correctly by now, you know it is hard sweat. What does that mean? That means the car C has only one vector. You get that? Which is the 0 vector. Do you get that? Is this still a vector subspace? Yes. Do you get that? Subspace should contain at least the 0 vector. Do you understand that? So what will be the basis for that vector space? The basis S will be equal to 0, 0, 0. Is that clear? Do you understand that? In this case, that's the only basis you can have. How about this? The dimension is 1. That's only one vector. Is that clear? The dimension of car T is 1. That means the nullity of the transformation T is 1. Do you understand that? So let's take another one. Alright, give this a try. It's the same problem. Again, look at the board, please. Be careful here. Listen, please. Again, you say that x equals a, comma, b, comma, c. Doesn't matter. You use this one next week. Okay. The elements of car t, which is an element of car t, to follow that t of x, which will now be t of a, comma, b, comma, c, should be equal to 0. So the 0 element in what? Rt should be equal to the 0 element in Rt. Which means that what is t of ABC? T of x1, x2, x3 is x1, 0, 0. That means t of ABC will be a, comma, 0, 0. That means a, comma, 0, comma, 0. Because the 0 element in Rt is 0, comma, 0, comma, 0. You get that? Alright, so what does this tell you? It tells us that a should be equal to 0. That's the only restriction. B and C can carry any value. Is that clear? That means B and C are going to be free variables. Is that clear? You understand that? Alright, so B and C can be any value. So we now say what? We now set B equal to, let's say, K1 and C equals to K2. Because they can be any values. Is it clear? You understand this idea? You understand it? Right. They are not necessarily 0. It can be just anything because whatever they are will not reflect 0. Is it clear? Okay, so I'm free to choose whatever value I like for them. Is it making sense? Alright, so therefore x is equal to a, comma, b, comma, c equals to a, which is 0, comma, k1, comma, k2. Pay attention, please. So how will I write this now? I want to write this, I want to factorize this. This will be equal to, I can bring out k1 into 0, comma, 1, comma, 0 plus k2 into what? 0, comma, 1, sorry, 0, comma, 0, comma, 1. You understand this idea? You understand this? So that means here I have two vectors that will form the basis. Is this clear? Is this clear? So I have the dimension of this. I have the dimension of car t to be 2. Is it making sense to you? Is this clear? Alright. So therefore car t is equal to the space containing elements x, which are all vectors in R3, such that x is equal to, so I'm going to write this as a combination of these two. X is equal to k1 into 0, 1, 0 plus k2 into 0, 0, 1, where k1 and k2 are any real numbers. That will be the definition of car t. Alternatively, I can write that car t is equal to the span of the set 0, 1, 0 and 0, 0, 1. Taking sense. So I can define car t in either way. Is it clear? Alright, so that means the nullity of this transformation is what? What's the nullity of the transformation? 2. Okay. A basis for car t will be what? 0, 1, 0, Abi, and this one. So that's in the set that contains the two elements. It means a basis for car t. A basis, pay attention, for car t is x equals to 0, 1, 0 and 0, 0, 1. Please pay attention. This is a standard basis. Listen. You know, if I give you an OBJ question, I can write this as an option. Listen, please, listen. I can have anything like this. Please pay attention. I can have something like s is equal to, let's let's say 0, 2, 0, and then I add this to 0, 0, 1 plus 2. They are actually the same. Do you understand what I just said? Okay, the multiples. So far I can factorize something out of this and still get this. And also I can factorize something out of this and still get this. Is it clear? They are the same. So that is that. Now, so let's move on with other examples. Alright, number 3. C of A plus BX plus CX squared equal to AX plus BX squared. Is it a linear transformation? Is it a linear transformation? No. It's a linear transformation. Yes. It's a linear transformation. Yes.
Where now?
How? How? Yeah, it's not linear. Yeah? The maximum power is 2. Hey. How do you know? Very good. So listen. It is linear. They cannot give you something that is not linear. Listen, please pay attention. This is a linear transformation. Please listen now. From the space, listen. This goes from the space P2 of X to the space P2 of X. You know what I mean by that? Polynomials of degrees, okay, not greater than 2. Is that clear? It takes in polynomials of degrees not greater than 2 and produces polynomials of degrees not greater than 2. Is it clear? Is this clear? Do you understand that? Alright, so basically what we are interested in, what we concern ourselves with is what? These elements here. A, B, and C. Is that clear? You understand that? So those are the inputs. These are just coefficients. You understand that? These are just coefficients. So I'm not concerning myself also with the x and x squared. Coefficients are just A and B. Is it making sense? Is that clear? Alright, so again, listen to this, listen. In this question now, they did not define the transformation this way. I can also define this transformation as a transformation that takes elements, please pay attention, from R3 and gives elements in R3. Please pay attention, such that C of A, B, C is going to be equal to, so in this case, this is going to give us, please pay attention to this, it's going to give us 0, A, B. You understand what I just said? You understand this? No. So I'm arranging the coefficients. So the one that is constant term coming first, the one that is coefficient of x comes second, the one that is coefficient of x squared comes third. Is it clear? And then in the result, the one that is constant term, not 0. Is that clear? The one that is coefficient of x, A, the one that is coefficient of x squared, B. Let's arrange them in that order. Is that clear? Is this clear? Alright, so I can deal with this as this transformation. So whatever you get from this transformation is the same. Is it clear? You understand that? So I believe everybody can deal with it. You have T of A, B, C to be equal to 0, A, B. Then to find out what is T and find the basis for T. Is it clear? So go ahead. The element of T, if that's the case, T of x, which is T of A, B, C, is equal to 0 element in R. Is that clear? Alright, so that is, what is T of A, B, C? 0, A, B. Equal to 0, 2, hello, listen. So definitely, A is equal to 0, B is equal to or C can be any number, right? C can be anything. So I can let C be equal to K. That there. Okay. Any K element of R. This is clear now. C can be any number. So if that is the case, our X
You don't have H.
X which is A,
No, you have to. Well, we do not have. We don't have.
and this will be what? K is 0, 0, is that clear?
We should do this to pick. So stressing. You did it down. To read the exam. Military exam. Now we are still doing those stupid questions.
You see what?
Like from the arrangement of T
Arrangement?
like I mean after you wrote
So we are doing
yes like B is it not picking
Inside.
on the side is what it is. But in the results, T of A, B, C. What we are interested in. T of A, B, C is 0, 0. You understand that? That's what I think is 0. So A will be 0, B will be 0. I mean, 0 equals to 0. Alright. Yeah. Of ABC that you are equating to 0. You are not equating X to 0. You are equating C of ABC to 0. C of ABC is 0, A, B. That is what you are equating to 0. Is it clear? Is this clear? The definition is that C of X must be equal to 0. That is what C of X is 0, A, is it clear? Okay, so listen. Assignment. Okay. For assignment, it is number 4. You don't know when you don't have Look at this last question. Look at this last question. T takes elements from M22, that's the matrix of 2 by 2, the space of 2 by 2 matrices. Do you get that? And produces 2 by 2 matrices. The first one takes the matrix A and produces its transpose. That AT means the transpose of matrix T. That so we want to find the kernel, like before, we find the basis of kernels, and also find the nullity of the transformation. So here, this takes in matrix A and produces KA, that is the multiple, the real multiple of A. Alright, so work with that, we will move on from there.